And we will slowly go to, of course, when the temperature of the tube has a different is different from that of our fluid, heat transfer occurs through convection, advection, and conduction. We need to consider to do similar considerations for our internal flow. Let's begin with easy case for laminar flow. And the Prandtl number larger than 1. I write it in this way. What's the typical case for Prandtl number larger than 1? Oh yeah, yes. What else?
Like anything that's more viscous.
Viscous, yes. Viscous then conduction, like what we did in our quiz 2, water, right? 7.56. How about molten metal? It's pretty tiny. It's like 10 to up minus 3. For Prandtl larger than 1, which boundary layer is thicker?
Viscous.
Yes. The Prandtl number given by ratio of kinematic viscosity over diffusivity. And which boundary layer associated with the kinematic viscosity? YCV, right? Which boundary layer associated with alpha? YCT, right? So for Prandtl larger than 1, automatically you would have viscous boundary layer thicker than thermal boundary layer. And then question, how about our fully developed thermal entry length? Which one is larger? Pipeline here and the center line. We know we already learned we have, when the two velocity boundary layer collide, we have our hydrodynamic entry length. And this is our YCV. For the case of Prandtl number larger than 1, which one is larger, thermal entry length or velocity hydrodynamic entry length? Yeah, because we already discussed thermal boundary layer is everywhere smaller than our viscous boundary layer. Until it gets merged at the center line. And we termed this as the fully developed thermal entry length. XFD and subscript T means thermal. And as we see, for some part of the tube, it contains both entry lengths. We termed those part, which is given by the smaller one of the entry lengths. For Prandtl larger than 1, that is the hydrodynamic entry length. We termed this as the combined entry, which contains both entry lengths. Of course, for Prandtl number smaller than 1, combined entry length is given by our thermal entry length. Right? And we will do the similar calculation as we obtain the correlations for hydrodynamic entry length. When it comes to thermal boundary layer, we have our YCT equals 3 square root. Instead of kinematic viscosity, we have diffusivity here times x of the T over what we have for our external flow. As you see there, here we have thermal boundary layer smaller than viscous boundary layer. The velocity in thermal boundary layer is not constant. We used some characteristic velocity to put there for our external flow and use triangle rules to obtain. What should we put there for our, as you see, when the two thermal boundary layer collide here, what's the velocity associated there? Typically, thermal boundary layer for in common heat exchangers is much larger than hydrodynamic thermal boundary layer. So once it collides here, I would suggest the velocity is also maximum at the point where it collides. Right? And of course, to calculate our thermal entry length is where the thermal boundary layer reaches to half of the tube diameter. And so for x FDT, we would have for laminar flow, the fully developed thermal entry length is given as 0.05 Reynolds number times that of our Prandtl number. This is given by equation 8.23 in our textbook. Here is the 0.05 Reynolds number. That is our hydrodynamic entry length. Then connected with the Prandtl number, we get our thermal entry length. Then for Prandtl number larger than 1, thermal entry length larger than hydrodynamic entry length. The equation speaks, right? We just given by our intuition, we know when the thermal boundary layer is smaller than viscous boundary layer, it takes longer to converge, and it reflects in the equation also. And that's for laminar case. For turbulence, we know that for hydrodynamic entry length in turbulent case, it's almost more or less like 10 diameter of that of the tube. How about for thermal entry length in turbulent case? The viscous boundary layer, it's almost the same as that of the thermal boundary layer that we already learned in external flow. Then, but when those two boundary layers are almost the same, which means our entry length is almost the same. So the fully developed thermal entry length for turbulence case is the same as that of the hydrodynamic, 10 diameters.